Welcome back to Chemistry 3120. Today's lecture 21, and today we're going to talk about cross-ester condensations. So we finished off this one. Today's focus, as I mentioned, will be cross-ester condensation. So up to now, for ester condensations, we've been looking at molecules where they're self-condensing. And you can imagine that's very useful, but there's going to be many instances where a researcher may want to take two different molecules and have them cross-react, similarly to what we learned with the aldol reaction. So similarly to aldehydes and ketones, care must be taken to understand which molecule will be the enol partner, the nucleophile, and which one will be the acylating partner, or in other words, the electrophile. Similar to aldehydes and ketones, care must be taken to understand which is the enol partner, aka nucleophile, and which is the acylating partner. AKA electrophile. So we try to avoid mixtures of different cross condensation products by employing a similar strategy to what we learned with aldol reactions. If you recall from aldol reactions, oftentimes some of the best enolizing or some of the best electrophiles were things like this that just couldn't enolize. So that's one example. We looked at other types of molecules where there wouldn't be any acidic protons on there. So similarly, we want to use esters that cannot enolize. So I'll draw four good enolizing partners, or good acylating partners that can't enolize, and they're all fairly reactive. Okay, so all four molecules are commercially available. So here you have like a diester, then you have this ester here, that's like an aldehyde. You have this compound here with sort of a mixed ester together, and then a phenyl ester. So all these don't have any acidic protons. As we go from right to left, we actually increase the electrophilicity. So these ones are really quite reactive. These ones are reactive, but not as reactive. So let's take a look at an example. And using one of those acylating partners. So the advantage is that you can put both of these in solution at the same time, and the goal is that you'll generate one product. So if you treat this with ethoxide, you know right off the bat that you'll generate an enolate, and then this enolate will react with this acylating partner. And this can't enolize, so this can only act as an electrophile. And this diester is more reactive than a simple ester, so you don't have to worry about this reacting with itself because this is the better electrophile. Here's our new carbon-carbon bond. And collapse your tetrahedral intermediate. Electrons will go down, kick off the ethoxide. And that's your product. Is that your full, complete mechanism? Think back to last lecture, right? These steps are all reversible, but by creating that new carbon-carbon bond, you now have a new alpha proton between two carbonyls. That makes it much more acidic. And since we are still in ethoxide basic solution, we need to form that delocalized enolate. As I'm showing you here, irreversible step, and then when you do the workup, step 2 with water, electrons will come down, and this will give you your product. Okay, so here's an example highlighting that irreversible step, but also using this great acylating partner that can't enolize. Just make a note here. Much more electrophilic. Compared to starting material ester. This one up here. All right, good. Let's make a few compounds. Make the following compounds. Okay, let's make this compound, and what we're going to do is we're going to make our carbon-carbon bond right here. Okay, so this is our carbon-carbon bond that we need to make. How are we going to make this using the strategies that we've learned? What's going to be the nucleophile? What's going to be the electrophile? Okay, so you can imagine on this side of the molecule, this has to be your electrophile, and on this side of the molecule, this is going to be your nucleophile. And your nucleophile is going to be this compound here, which once we add base will enolize, and that's going to be your nucleophilic enol, or enolate. So let's actually draw out how we could make this compound. So what would be a good base to use in order to make this a nucleophile? A good base to use would be again, something like sodium ethoxide, because that has the same side chain as the ester does for this one. So sodium ethoxide and ethanol. So you can imagine that you'll form the enolate like we've done over and over again, and then this portion here is our electrophile. So what are we going to add in order to make that electrophilic? Well, something like benzyl halide, benzyl chloride, or benzyl bromide would work really well. Okay, so if you do this reaction, you will generate product A. If you're not convinced, then on your own, after this video, try the mechanism on your own. Number 2, or letter B. Make this compound and here you have to think about where is our carbon-carbon bond, or key carbon-carbon bond during this Claisen ester condensation. Now you might say, well, let's do something similar to what we've done here, where we take this compound, form the nucleophilic enolate, then have it react here. If we do that, then this has to be our electrophilic carbon, and that's very challenging to do because that's an sp2 carbon, right? That's very different from a benzylic sp3 carbon. So rather than making this the key carbon-carbon bond, let's make one of these, they're both equivalent, the key carbon-carbon bond. So if that's the case, let's start with what the nucleophile is and what the electrophile is. If we cut this bond here, everything on top is going to be your nucleophile. So you can imagine that you're going to have this as your starting material, and then again we add a base in order for this to become an enolate. Okay, so here we are picking up the proton, forming the enolate. And then what is our acylating partner going to be? Okay, we need to form a carbon-carbon bond like this, carbon-carbon bond. Okay, so you can see here, if I actually draw out what that looks like, carbon, we need to form this as an electrophile, but you need something good as a leaving group here. So a good compound to use, if you look at your checklist here of compounds that we've looked at, this would make an ideal compound because you have two ethoxides on both sides. So therefore, what we can do is we can react this with this compound here, which is a pretty good electrophile. It's going to be better than this starting material here because we've learned about electrophilicity. So when this comes down and reacts, you're going to generate exclusively that one product. So I'm just showing you the mechanism. Okay, so you have this carbon with an O- tetrahedral intermediate, OET, OET. This comes down, kick off one of them, they're both the same, and you generate product B. So with this one here, you can actually mix this compound with this compound together with base, and that will give you the desired product. Okay. Let's go through just one more Well, one question here. Which is sort of similar to what we've been doing, but the more practice we get with this, the better. So this is a simple, just predict the product. Don't need to draw a mechanism. You can on your own time if you'd like, but what is the product going to be? Ethoxide base, it's going to form an enolate, then this negative carbon will react here, electrons go up, come back down, kick off ethoxide, then you'll do that irreversible deprotonation, and then you'll pick up the proton. So your product will look like that. Okay, for this one, we're going to be asked to draw the mechanisms for the major and minor product. All right, so this is our puzzle here. We have this ketone reactant with this acylating partner with base. What are the major minor products? Draw a mechanism for that. You can see here, because we have an asymmetrical ketone, we're going to have two different types of enolates. So why don't we start with this one here. We'll just call it HA. And we know that will generate an enolate quite readily. And then your enolate will come react with the acylating partner. Generate this, electrons will come down. Generate this. In terms of a mechanism, right, all these steps are reversible. But you know you have this acidic proton here. So what you're going to do is you're going to form that irreversible delocalized enolate. And then when that forms and you do the workup step, step 2, pick up a proton. And your final product will be this one. Okay, so that's one scenario. If we take HA, let's look at scenario if we take HB. Take HB, you form an enolate like this. This will react similarly to like I'm showing you up there. Electrons come down. And then here you will collapse the tetrahedral intermediate. And this will be your compound here. Mechanistically, you know all of these steps are reversible, right? You get to this point, you say, yeah, I know it's reversible except for that irreversible step. And you try to take a proton here, but don't do that because there are no acidic protons here, right? These are two methyl groups. Don't make that a Texas carbon. Can't have 5 bonds. So because there's no irreversible step during this reaction, you will form this, but it will be in low yield. So this will be your minor product. Whereas this one up here will be your major product. And interestingly enough, you could take a look at both enolates and say this is the less substituted enolate, the kinetic enolate, less stable, right? But it leads to the major product. Whereas this enolate here is more substituted, thermodynamic, more stable, but it leads to this minor product. All of these steps are reversible. So while this might be more stable, it's not going to lead anywhere super productive, so it's going to go back, and this is going to be your irreversible sink. Excellent. So let's just quickly summarize what we've learned about beta keto esters. So here is a compound, right, that you could potentially make. And we kind of started off with a similar type of strategy last lecture, so lecture 20, and then you could see 2 different ways to make this molecule. Now, with the knowledge we've gained from esters and condensations and acylating partners, we're going to find that there's a better way and a not so optimal way. So let's take a look at a scenario here if we create our carbon-carbon bond through this means here. So if we do that, our nucleophile is going to be this. So let's call this A, pathway A. Our nucleophile is going to be this, right? When you enolize it, it will become the nucleophile, and then your electrophile will be everything on this side as an ester. Okay, so that's scenario A. Scenario B is going to be creating that carbon-carbon bond right over here. So your nucleophile is going to be everything up here. And your electrophile is going to be this, but as like a diester. Just to make it clear, let's write out our electrophile and nucleophile on pathway A as well. Okay, so two different ways to make this molecule, A or B. So which one is going to be the better way? If you look at pathway A, and if you mix these two together, you can imagine they're both equivalent esters. They're both going to enolize in a similar fashion. And you're going to get a bunch of cross products as well. It's going to be hard to get simply that one isolated product. In contrast, scenario B, you have just one type of nucleophile and you only have one type of electrophile. This acylating partner cannot enolize. Okay, so in other words, pathway B is the appropriate way to do this. I'll say that's yes. Let's say yes for that one. Whereas pathway A, no, it's not ideal. You're going to generate a mixture of different products. Okay, so some key questions to think about whenever you're designing these syntheses. One, will the correct carbonyl compound enolize? In both these cases, yes, this will enolize, but in this case here, yes, this will enolize, but this one will also enolize. So you have a competition there. Number two, if it's a ketone, will it enolize in the right orientation? So these are some other important considerations to think about. Are you going to have a situation where you have an asymmetrical ketone, for example? Then you have to think about how to influence and how to generate one-sided enolate versus a mixture of both. Will it enolize in the right orientation? And if we take a look at our situation here, where we actually want to form an enolate at this position, not this position, therefore we don't want to use a base like LDA, which would actually only create the kinetic enolate and take the least sterically hindered proton. We'd want to use some type of reversible base that would generate our transenolate and give it more time to equilibrate that so we can get our product. So you have to think back to our discussion that we had with cis and transenolates. Number three, once you generate the enolate, will it react with the acylating partner? Right. So if you generate an enolate here, will it react here? Well, yes, it will, but it will also react with itself. So you have a competition and a mixture of compounds. Whereas here, once you generate your enolate, this is the only acylating partner there. Will the enolate react with, let's see if I can fit this in, with, okay, just follow me here, the right acylation partner. Okay, and then there's a little question mark here. Okay, will the enolate react with the right acylation partner? So these are just some key questions that we think about when we're designing these syntheses. Sometimes there isn't a perfect solution, and we have to take the best one and hopefully get our compound in sufficient yield after purification. Okay, so that concludes lecture 21 on cross-ester condensations. Next up, lecture 2, we'll look at intramolecular cross-Claisen condensations. See you for that one.